Subscribe to the Java Tech Learning channel to learn more about new videos. Hi guys, this is Vishal. Since long time I have not uploaded any content, so here I am. In this video, I'm going to answer some of the most frequently asked Apache Kafka related interview questions. I have listed down few important questions which essentially covers architecture, features, benefits of Apache Kafka. I believe if you're preparing for a job interview and you got Kafka mentioned in your skill set, then you should be going through these questions. So let's go through each question one by one. First question is, what is Apache Kafka? It's very simple question. Nowadays nobody asks this one, but we will go over it. Apache Kafka is an open source distributed streaming platform for processing large amount of streaming data for real-time applications. It is designed for high throughput, fault tolerant and real-time data streaming and messaging purpose. Apache Kafka is widely used for building data pipelines, event-driven architectures, real-time analytics, etc. Next question is, what is the difference between Kafka and traditional message brokers like JMS? Well, I have listed down the differences based on the feature it offers. And the first, data streaming. Apache Kafka is primarily designed for data streaming and real-time event processing. It excels at handling large volumes of data and provides a distributed log-based architecture for event-driven applications. On the other hand, traditional brokers like IBM MQ, RabbitMQ are the point-to-point messaging and publish-subscribe messaging patterns. They are typically used for reliable messaging between applications and systems. Next point is message persistence. Kafka retains messages for configurable period, allowing consumers to rewind and replay messages. It is often used as a data store for event sourcing and streaming processing. Kafka's message storage is a log-based, providing strong durability guarantees. JMS usually persists messages for shorter duration and primarily focus on ensuring reliable message delivery between sender and receiver. Next point is scalability. As you know, Kafka is horizontally scalable and designed for handling high throughput, making it well suited for scenarios with massive data stream and real-time analytics. While on the other hand, JMS have some degree of scalability, but they may require more complex setup in order to achieve the same level of scalability as Kafka offers. Now next point is about use cases. Apache Kafka used for log aggregations, data pipelines, event sourcing, real-time analytics and building event-driven architectures. While on the other hand, traditional brokers like IBM MQ, RabbitMQ are used for reliable communication between enterprise applications, especially in scenarios where transactional messaging and guaranteed delivery are critical. Some of the new features which Apache Kafka offers are like partitioning, data replication, message order guarantees. These are some features which JMS don't offer. That's why in today's world, for handling a large volume of data and for the low latency applications, we prefer Apache Kafka. Third question is, what are the key components in Apache Kafka? In other words, it can be asked like, explain the architecture of Apache Kafka. So first we'll go over the components present in the architecture and then we'll see where each component fits in the architecture. Alright. So the first component is brokers. Kafka server is also known as a broker. It's a bridge between producers and consumers. Brokers receives data from producers, store it in the topics and serve it to the consumers. It also manages topics and partitions. Kafka can have multiple brokers for scalability and fault tolerance. Next component in the architecture is Zookeeper. It's a centralized service for maintaining Kafka cluster metadata. Kafka has moved away from a direct dependence on the Zookeeper for newer versions. In newer versions, Kafka has its own internal metadata management. But for the older versions, we still have a Zookeeper component there in the architecture. Okay. Then we have topic. Topic is a logical channel of stream of data. Producer publishes data to the topic, same data is consumed by consumer. Topics are divided into partitions to enable parallel processing and distribution of data across brokers. Producer. Clients that publish data to the topic is called producer. Producer can be written in any technology. It can be a Java producer, it can be a producer written in the Spring Boot, it can be a source connector, etc. Last one is consumer. Consumer is the client that subscribes to topics and receives data from it. Again, it can be written in any language like Java, Spring Boot, Kafka listener, or Sync connectors. Now let's go over where each of this component fits. Here you can see this is a simple architectural diagram of Apache Kafka. On the left hand side we have a producer like producer 1, producer 2, producer 3. We can have a multiple producers in the Kafka, right? It's just a client which is producing a data to the specific topic. On the right hand side we have a consumer similar to producer. They are consuming the data. Okay, they're subscribing to topics, they're subscribing to partitions. We'll understand what is the partitioning in a topic is, but here they are subscribing to the topics and reading the data for further business logic. Okay, the central part is called the Kafka cluster. Why? Because Kafka is a distributed architecture and it can have multiple brokers. So the unit of multiple broker is called Kafka cluster. Okay, here we have three brokers like broker 1, broker 2, broker 3 are responsible for handling all the communications happening between producer and consumer. And last, here we got Zookeeper. Zookeeper is responsible for maintaining all the metadata, all the communication metadata happening. Alright, so this is the simplest diagram. If somebody asks you to explain in the diagram, this is the best way. So the next question is, what is Kafka partition and what's the purpose of it? Well, it's a process of breaking a topic into multiple fractions, which is also called as partitions, each of which can live on a separate node or broker in the Kafka cluster. The number of fractions is determined by us or by the default cluster configuration. This way, the work of storing messages, writing new messages, and processing existing messages can be split among many nodes in the cluster. Kafka guarantees the order of the events within same topic partition. However, by default, it does not guarantee the order of event across all partitions. The purpose of partitioning is to enable parallelism and increase throughput. So here, let's say we got three partitions, partition A, partition B, partition C for a topic. On the left hand side, we got a producer which is publishing message across all three partitions. On the right hand side, we got two consumer within a consumer group which are subscribing to this partitions. Alright. Now here, as you know, messages in the topic are always published in the form of key and value. That is why here you can see keys are mentioned like keys A, key B, key C. Messages with key A lands in partition A, messages with key B lands in partition B, and same for C. Now when a Kafka guarantees the order of events within the same topic partition, that it means consumer receives the data from the partition in the same order in which producer publishes. Okay, so when consumer receives the data from partition A, it is receiving in the first order basis. Okay, so this is how partitioning works. Next is, what is Kafka offset and what is Kafka commit? Well, they're actually closely related to each other, but first understand what is Kafka offset. It's a unique identifier or a pointer of a message or a record within a partition of a topic. It represents the position of the consumer in the partition. For example, current offset of a consumer is 5, means it has consumed records from offset 0 to 4 and will receive a next record with offset 5. Offsets are unique within a partition but not across partitions or topics. Each consumer maintains its own offset for each partition it is consuming from. This means that different consumers can be at different position within the same partition or a topic, allowing for independent and parallel processing of the messages. Kafka commit is an act of confirming that a consumer has successfully processed and consumed a batch of messages up to certain offset within partition. Let's take the same example that we talked about a Kafka offset. Current offset of a consumer A is 5. It can be confirmed only when Kafka performs commit operation to inform a zookeeper that consumer A has successfully received records from offset 0 to 4. Alright? Committing offset is important for ensuring that in case of consumer failure or system crash, consumer can resume consuming the messages where it left instead of reprocessing the messages again. Kafka provides two main approaches for committing. One is a manual commit, one is a auto commit. By default, auto commit is enabled. So here, as you can see, we got one producer which has been writing a data to the topic, and it is writing at position 12. And we got a two consumer A and consumer B, which is subscribing messages from the topic at its own pace. Okay, consumer A at right now is at offset 9. That means it has successfully received the record from 0 to 8 and perform commit operation. Similarly, for consumer B, which is at offset 11, that means it has successfully received the record from position 0 to position 10. So as and when producers keeps writing the data to the topic, consumer A and consumer B will keeps on subscribing and reading the messages. So this is how Kafka offset and Kafka commit works. Next question, which is similar in line to the last one, what is the difference between manual commit and auto commit? So let's first understand auto commit. Here, consumer periodically commits offset automatically based on the configured interval. So default interval is 5 seconds. This is the simplest way to commit offset by just setting enable.auto.commit property to true at the Kafka consumer side. This is a property which Kafka library has provided to us in order to enable auto commit. By default, it is true. We can also change the default commit interval by setting auto.commit.interval.millisecond to specific value. Like we got a default interval as 5. If we want to change that, we can set by using this property. Sometimes auto commit could also lead to duplicate processing of records in case consumer crashes before the next auto commit interval happens. Let's say default commit interval is 5 seconds. So at X seconds, Kafka commits the offset. Next happens at X plus 5 seconds. Before X plus 5 occurs, within the time, if Kafka consumer crashes, then it will start reprocessing messages from the last committed offset. So which could lead into duplicate message processing. So that's the bit of a flaw we have in the auto commit. That's why Kafka offers the second option, that is called manual commit. Manual commit can be enabled by setting enable.autocommit false. Okay, here consumer explicitly commits offset using commit saying or commit async methods provided by the Kafka client library. Commit sync is a synchronous commit, and it will block all the threads until either commit succeeds or an unrecoverable error is encountered. While on the other hand, commit async is a asynchronous commit operation. It won't block any thread. If any error occurs, then it just simply passes to the callback method. Next question, explain the Kafka log retention mechanism and its configuration. Retention period refers to the length of time that messages are kept in a Kafka topic before they are discarded. By default, Kafka retains data for 7 days. In simple word, it is nothing but about expiry. Messages in Kafka topic cannot be present there forever. It has to have some expiry. So the default expiry is 7 days. This is specified by log.retention.hours parameter in the broker configuration. It's a property provided by broker, which is set to 168 hours. That actually means 7 days into 24 hours. Retention period can be adjusted according to the needs of your application. It is based on your requirement. Default is 7 days. It can be lower than that or it can be higher than that. Kafka supports server level retention policy that can be tuned by configuring exactly one of three based configuration properties. One which we saw, log.retention.hours or log.retention.minutes or log.retention.milliseconds. Kafka overrides lower precision value with a higher one. So log.retention.millisecond would take highest precedent. So if you set log.retention.hours like 7 hours, log.retention.minutes to something more than 7 hours, and if you're setting log.retention.millisecond to 7 days, which something x value in a millisecond, then that millisecond takes highest precedent than rest two properties. Okay. If the log.retention is set to 5 days, then the publish message available for the consumption for 5 days after it is published. After that 5 days, message will be discarded to free up spaces. Point to note here that the performance of the Kafka is not affected by data size of the messages. So retaining lots of data is not a problem, but also retaining lots of data for no reason is not a good practice. So we should have some fixed specific retention period set based on your business requirement. Next question, explain the role of Kafka producer and consumer. Kafka producer is responsible for publishing data streams to one or more topics in the Kafka cluster. Producers can publish data from various sources such as applications, databases, sensors, or file system, etc. The primary responsibility of the producer one is data serialization. Here, to serialize the data into a format suitable for transmission over the network and storage in Kafka. Second is load balancing. Producers automatically distribute data across partitions of topic based on record key, ensuring effective parallelism and scalability. Last, durability and availability. Producer handles scenarios where Kafka brokers are unavailable or fail during the publication, ensuring data durability and guaranteed delivery. Kafka consumer responsible for reading data streams from one or more topics in the Kafka cluster. Similar to producer, it has its own responsibilities. First one, deserialization. Consumers deserialize the data received from the Kafka brokers into a format that can be processed by consumer application. For example, the widely used format for any Kafka pushing the messages into Kafka topic is Avro format. Next is offset management. Consumers keep track of their position in the log or offset for each partition they are consuming from, allowing them to resume a consumption from the last committed offset in case of failures or restarts. Third is group management. Consumer can be a part of a consumer group to distribute partition among themselves. Within one consumer group, there can be multiple consumer instances, and that bunch of consumer instances called a group, and partitions of a topic can be distributed across these instances. Last one is the data processing. Processing the data received from the Kafka, applying transformation like filtering, aggregations, or integrating with other systems or applications. So here is a simple example of creating a producer in the Java. Okay, so first part, like I said, we got the serializer for a key and value. It is using string serializer. Then it is initializing Kafka producer with that properties and using the producer.send method to publish the messages into the topic. Here we have mentioned the topic name and the message. So accordingly, it is publishing the message. At the end, it is flushing and closing the producer. This is the simplest example how to write a producer in the Java. It can be written in the Spring Boot application by using the property configuration and etc. But this is just one example. Similar to producer, we got an example of consumer written in a Java. Here properties are being set like group ID, deserializers. Then here Kafka consumer is initialized with that properties. Then calling a subscribe method on the specific topic, which topic you want to subscribe, and on the while loop we are calling consumer.poll to read the data from the topic and perform the business logic on it. Alright. Next question, what is Kafka producer callback and why would you use it? Kafka producer callback is a method that you can implement to handle responses from broker asynchronously. This is useful because Kafka producers are asynchronous in nature. So when you send messages using Kafka producer, the send method you use simply adds the record into a buffer of pending records and returns immediately. This allows producer to batch messages together for efficiency. However, you might want to know what happened to the record you have published, such as whether the data was correctly published or not, where it was published, its offset, partition value, etc. This is where callbacks come into picture. We can overload the Kafka producer send method with an instance of callback interface as a second parameter. So here we got an example of send method with the two parameters. One is the message you want to publish and second is the callback interface. So here callback interface is implemented, on completion is overridden. On completion method has a two parameters, record metadata and exception. If exception is null, that means message is successfully published, and metadata provides which topic it published, which partition it published, and what is the offset number. If exception is not null, that means there is error occurred while sending message or while publishing the message. So you can have the exception here. So this callback interface is provided to take appropriate action based on the outcome of the message production. Next question, explain the Kafka producer acknowledgement. Well, in Apache Kafka, producer can choose to receive an acknowledgement of data writes. This acknowledgement is also known as a confirmation. There are three acknowledgement modes available. First, x equal to 0, second x equal to 1, last x equal to all. First, x equal to 0. Here producer simply sends the data and does not wait for any acknowledgement. This can be a possible data loss because if the broker is down, producer will not know because it will not get any acknowledgement. Second, x equal to 1. So this is the default setting as of 2.0 Kafka version. Here producer requests acknowledgement only from leader and leaving replicas. If an acknowledgement is not received from leader, then producer has to retry. If acknowledgement received from leader, then it says message is successfully delivered into topic. Okay. Third one, x equal to all. Here producer requires acknowledgement from both leader as well as replicas. If it does not get response from leader and all replicas, then producer will retry publishing messages. So here there is absolutely no data loss. Next question, how can you scale a Kafka consumer to handle higher loads? Well, there are several ways to handle higher loads in a Kafka consumer. I have listed down some important points. First is partitioning. Kafka topics are divided into partition, as you know, and each partition can be consumed by only one consumer within a consumer group. You can increase the number of partitions for the topics being consumed, which allows more parallelism in processing. Second point, similar to that, now that you have increased the partition on the topic, same way you can increase number of consumer instances within a consumer group in order to leverage the benefit of parallelism. Kafka ensures that each partition is consumed by only one consumer within a consumer group. So adding more instances will distribute the load across them. Okay, so if you have more partitions, you need to have more consumers. Then we can optimize the performance by tuning some configuration parameters, adjusting some properties like fetch mini bytes, fetch max bytes, max poll records, and max poll interval. This will bring the balance between throughput and resource utilization. Then last one is optimizing message processing. This ensures the message processing logic in your consumer application is efficient. This includes minimizing processing time, avoiding unnecessary operation, and using asynchronous processing wherever possible. By following these steps, we can scale a Kafka consumer to handle higher loads. Next question, what is Kafka consumer lag and why is it important to monitor? Kafka consumer lag refers to the difference between the offset of the latest messages inserted in a Kafka partition and the offset of the last message that has been consumed by a consumer. It represents the number of messages that consumer is yet to process. Now, why is it important to monitor? Well, in a real world scenario, production support team will always keep an eye on this consumer lag. Couple of reasons I have highlighted. First, identifying bottlenecks. High consumer lag can indicate that the consumer is struggling to keep up with the rate of incoming messages. This could be due to different issues with the consumer application itself, like resource constraints, CPU, memory, network, etc. Second is preventing a data loss. If a consumer falls too far behind and the retention period kicks in, then there is a risk of data loss. Messages removed as a part of retention will no longer be processed. Third, ensure timely processing. For applications that require near real-time processing of data, high consumer lag can lead to increased latency and delayed response time, potentially impacting systems' overall performance and user experience. Fourth is load balancing. In a consumer group, monitoring the lag for individual consumer instances can help identify if the load is evenly distributed across them. If some consumers are falling behind, indicating that there is a need for rebalancing or scaling the group. Capacity planning. Tracking consumer lag over the time can provide insight into message throughput patterns, help plan future capacity requirements such as the scaling number of consumer instance rate or adjusting the hardware resources allocated to that particular consumer application. Last one is alerting and troubleshooting. By setting the appropriate thresholds on consumer lag, alerts can be triggered when the lag exceeds certain level. This allows proactive monitoring and investigation of potential issues. This is where generally in a real world, alerts has been set based on the consumer lag. If the lag increases beyond the threshold, production support team will come to know and it will take an appropriate action. Alright? Next question, what happens if consumer fails to commit offset? If consumer fails to commit offset, then it leads to several potential issues. First one, duplicate message processing. When consumer fails to commit offset, it may start reading the messages from a topic from the last committed offset. This can result in duplicate message processing by consumer, leading to data inconsistency or incorrect application behavior. Second one, loss of message ordering. Kafka guarantees message ordering within partition. But if a consumer fails to commit offset and reprocesses message, it may disrupt the order of messages consumed by downstream applications. Third, increasing consumer lag. If consumers are not committing the offset on timely manner, then consumer will fall behind on the latest offset in the partition, leading to the increased consumer lag. Last one, inconsistent consumer group state. Failed commit offset can result in an inconsistent group state where some consumers have committed offset while others have not. This can lead to a rebalancing issues and uneven distribution of partition among consumers within group. Next question, explain the Kafka replication protocol and its guarantees. The Kafka replication protocol is responsible for maintaining multiple copies or replicas of partition across brokers in a Kafka cluster. It provides several guarantees to ensure data durability, consistency, and fault tolerance. First one is a leader-follower replication model. Kafka uses leader-follower replication model where each partition in a topic has one leader and 0 or more followers. Leader is responsible for handling all the operations like read and write for that partition, while followers simply replicate the leader's data asynchronously. Second, replica synchronization. When a leader receives a produce request, it first appends the message to its local log and then asynchronously replicates the message to its followers. Followers pull the data from the leader using a fetch request protocol. The leader sends a batch of messages to its followers and followers acknowledge the messages once they are successfully replicated. Third, in-sync replicas. Kafka maintains a set of in-sync replicas for each partition. These are the replicas that are fully catch up with the leader's log. These replicas ensure that the partition can continue to function even if some replicas fall behind or become unavailable. Next is leader election. If the leader of the partition becomes unavailable, maybe because of the broker failure or some other else reason, Kafka triggers leader election process to select a new leader from the in-sync replicas that we got. This ensures that the data availability is not compromised even in the event of leader failures. Last one, durability and consistency guarantees. Kafka provides strong durability and consistency guarantee. Once a message is successfully written to the leader's log and replicated to all replicas, it can be considered durable and will not be lost even in the event of node failures. That is why these days Kafka is widely used because it's a fully distributed architecture. Again, it got leader and replicas model, so data will always be there and it will be durable and will never be lost. Next question, what are the different delivery semantics in Kafka? Well, Kafka supports 3 delivery semantics: at most once, at least once, and exactly once. These delivery semantics are nothing but to determine how messages are produced within producer and consumer. Alright, so the first one, at most once delivery. Here, message produced by producer is either delivered and processed only once or not at all. Producers do not wait for any acknowledgement from brokers. Hence, there is no guarantee that message will be processed, as it may be lost or discarded due to various reasons such as broker failure or network issues. This mode is suitable for scenarios where message loss is acceptable and low latency is crucial. Alright. Second one, at least once delivery. Here, Kafka guarantees that message will be delivered and processed at least once. Here, producer waits for an acknowledgement from Kafka broker after sending a message. Okay, if a message is not acknowledged within a specified time period, then producer retries sending it. It is possible that message may be processed multiple times due to retries or reprocessing. At least once delivery is suitable for use cases where duplicate message processing is acceptable or can be handled by making the consumer processing logic idempotent. Last, exactly once delivery. This is the strongest delivery semantic where Kafka ensures that each message is delivered and processed exactly once, even in the case of failures. This mode is achieved through Kafka's transactional support, where ensures that both message production and consumption are part of the same atomic transaction. Producer use transaction to write messages to Kafka topics atomically, ensures that message is either fully committed or fully rolled back. Consumers use idempotent processing and transactional offset to guarantee exactly once processing. This semantic is suitable for use cases that require a strict data consistency and cannot tolerate a duplicate processing or data loss, such as financial transactions, trading management, etc. Next question, what are Kafka streams? Well, Kafka streams is a client library for building real-time, fault-tolerant and scalable stream processing application on top of Apache Kafka. It is part of Apache Kafka project and provides lightweight and easy to use API for performing stream processing tasks such as data transformation, aggregation, filtering, joining, etc. Key features of Kafka streams include stateful stream processing. Here, it provides built-in support for stateful stream processing, allowing applications to maintain and query state as they process data streams. State can be stored locally within application or backed by external state stores such as Apache Kafka Stream State Store or external DBs like RocksDB. Examples of stateful operations like windowing, aggregations, etc. Second, exactly one semantics. Kafka Stream offers support for exactly one semantics, ensuring that data processing is idempotent and resilient to failures. Third, high-level DSL and processor API. Kafka Stream supports both high-level DSL, that is domain-specific language, and low-level processor API for defining stream processing topologies. The DSL simplifies the development of common stream processing tasks such as a map, filter, group by key, aggregate, join, while the processor API offers more flexibility for custom stream processing logic by allowing developers to define their own processing nodes within the processing topology. Last one, fault tolerance and scalability. It inherently fault tolerant and scalable. Actually, these features are coming from Apache Kafka, leveraging Kafka's distributed nature and built-in replication mechanism. Last question we got, how does Kafka handle data security and encryption? Where it provides several mechanisms to handle data security and encryption. First, encryption in transit. Here it supports SSL or TLS encryption for communication between clients and brokers, as well as communication between brokers in a cluster. By enabling SSL and TLS, all data transmitted over the network is encrypted, protecting it from unauthorized access. Client authentication can be configured using SSL or TLS client certificates or any other mechanisms like SASL. Second, encryption at rest. Kafka supports transparent data encryption at rest. What does it mean? It means data stored on a disk is also automatically encrypted. Encryption at rest protects data from unauthorized access like disk theft or unintended exposure. Third, authentication and authorization. Here it provides mechanism for client authentication. As we saw in the first point, client authenticated using client certificate. Once authenticated, clients can be authorized to perform specific actions like read, write, etc. on topics and clusters using access control list. We also call it as a ACL permissions. Last one, data integrity. Kafka ensures data integrity by using checksums for messages stored on the disk. This helps detect and prevent data corruptions or tampering. So these are around 17 to 18 interview questions I have answered. I understand these are not enough to face an interview panel, so I'm going to provide some more practical and scenario based questions related to Kafka, Confluent, Kafka Streams, which I personally faced during my interview round. I want you to go through it, find the answer and practice yourself. If you think you need any help, then you can always reach out to me. Thank you.